2 points.
I don't know. No, I don't want to go on this right.
As long as
Because he likes me. That's not bad. It's not as like I guess it's not.
All right. So on Tuesday, tomorrow, we will have our quiz. No calculator quiz over just chapter 4. So we'll kind of spend a little time just going through that stuff. The majority of the questions, or half at least, deal with these 3 theorems. All right, probably more than half. Deal with these 3 theorems. So we had, and 3 of the questions you know for sure. State the theorem. Okay, so we've got to state the 3 theorems. And make sure you get them, the right one with the right name. Okay? You can kind of tell because of the name. Extreme value means extreme values. Max is a min. So if f is a continuous function over a closed interval AB, then f has both a max and min value somewhere in that interval. Okay? Now, we also know that we would look where for those max and min values? Endpoints, stationary points where the derivative is 0, and where the derivative is undefined. Right? Those are 3 places. Now, you could call a critical point, and 2 of those you can lump together as critical points, right? Where the derivative is 0, where the derivative is undefined. But that's not part of the extreme value theorem. Okay, the extreme value theorem just guarantees that if it's continuous, no breaks, no gaps, no jumps, on a closed interval, there will be a max and min. Then that other stuff is just, here's where we would look to find it. And that's what we did for optimization problems. So, okay? All right, a horizontal line. Yeah, what if you just had a horizontal line at 2? That's continuous. Yeah, what's the max? 2, the min? 2, right? Because it's a max because there is no value bigger than it. And it's a min because there is no value smaller than it. So it's both, and that's okay. And also there can be more than one, or it can happen more than once. So like for the sine function, no matter what closed interval you pick, it has a max value of 1. Well, at least if you go through one cycle. At least if you have 2 pi or bigger closed interval, then the max value would be 1, and the min value would be -1, even though it happens a whole bunch of different times. But we usually don't ask where the max is. We ask what is the max value. So we usually are interested in the y value. Okay, the intermediate value theorem says that if f is continuous over a closed interval AB, so same, whoops. I wasn't even touching the board. All right. So the intermediate value theorem, intermediate, think between, so it's values between, and the key is it's between where? What's the key to the intermediate value theorem? It's the points between the endpoints, f of A and f of B. So even though this function here, okay, has maxes and mins, above 2 and above 4, the intermediate value, or excuse me, let's give this a value. Let's say this is 3. Let's say this down here is -2. Okay, even though it has max higher than that, min lower than that, the intermediate value theorem says it has to hit all the y values between what? -2 and 3. It has to hit all the values between -2 and 3. We don't care that it goes higher or goes lower, that doesn't matter. Okay? It hits all those in between. And the way they say it a little different than that. I don't want you, somebody asked the other day about does it have to be, what if we leave out one word? Well, it depends. If you left out the word continuous, yeah, that'd be a big deal. But if you reworded a couple of the smaller words in there, if it was reworded a little bit, as long as it has exactly the same meaning, then you're okay. But don't say if it's continuous on a closed interval, it has to hit all the y values or something like that. That would not be specific enough. That's a good way to think about the intermediate value thing. Okay? But we want to be more specific. And what it says is if you pick any k in between f of A and f of B, there will be some input that will give you that output. Okay, that's what it's saying. pick any k, any y value in between here, there'll be some place where the output equals that. Okay, that's the same way of saying it's going to hit all those y values in between. So one is just a good way to think about it, but the other is more specifically how you say it. So there's a certain amount of memorization here for sure. All right, and then the one we learned on Friday, the mean value theorem. If the function is continuous on the closed interval AB and it's differentiable on this open interval, then there exists a C in between A and B such that f prime of C equals f of B minus f of A over B minus A, which basically says that the average rate of change is equal to the instantaneous rate of change. Now, you can say that, but you better have this equation in there when you do the mean value theorem. And the other difference in this one from the other two is we add differentiable. And remember, it's like the square and the rectangle. The first two are like the rectangle, you know, 4 sides, 4 right angles. But we add one more restriction to it, a rectangle can become a square. Not all rectangles are squares, but all squares are rectangles, right? Not all continuous functions are differentiable, but all differentiable functions are continuous. Okay? Differentiable means it's continuous, no gaps, no breaks, no jumps, none of that, and the derivative exists everywhere. So absolute value, the V-graph would be a good example. The V-graph is continuous, but it's not differentiable. Okay? So you add in that there can't be any sharp points to make it differentiable. Okay? Along with no gaps, no jumps, that kind of stuff. Okay, so there could be some questions about that, about the difference between continuous or differentiable, or just what's it mean to be a continuous function? So what's it mean to be differentiable? So think about that. So anyway, the mean value theorem basically would say this. If we slide the x along here, here's the slope, but the blue is the slope between the two endpoints, so that'd be the right side of our equation. Okay, the slope between the 2 points. Mean value theorem says somewhere in there, there has to be that same slope. Okay, so here's one place right there, and there's another one, probably at least one more here. And then we did that thing with the calculator on Friday. We did the thing with the calculator on Friday where, you know, we showed some, and, you know, sometimes it has multiple places. But the mean value theorem says there has to be at least one. Common sense way of thinking of it, if we average 60 miles an hour, at some point we had to have been going. Instantaneous rate of change. We had to have been going 60 miles an hour at some instant. Okay? And then the other thing that's good for, we did a proof of one of the chart things where it connects f prime and f. And that's another reason why mean value theorem is important. Okay, let's go through your homework questions again on page 287. Now, they were talking, they went into some stuff that didn't really have anything to do with the mean value theorem, but it does have to do with this idea of theorems in general. The hypothesis, the conclusion, the if and the then. Okay? If it's raining, then it's cloudy. The converse would be if it's cloudy, then it's raining. First one, now we could argue about it probably. If it's raining, then it's cloudy. Let's just say that's true. If it's raining, then it's cloudy. Okay? But if it's cloudy, then it's raining, that would not necessarily be true. Okay? Number 3, if x is greater than 2, then x is greater than 1. That would be true. Turn it around. If x is greater than 1, then x is greater than 2. That would not be true. 5, if f prime of x equals 2x, then f of x equals x squared. What do you say for that, true or false?
False.
That's false, because you got the plus c on it. Okay? It could be one of them. It would be a possibility, but it's not true that if the derivative is 2x, then f had to be x squared. That's not true. But you turn it around, it is true. If f of x equals x squared, then the derivative would be 2x. Okay, so just some stuff with that. On 8 through 11, we had this stuff. Number 8 said, find a function with these properties, 2 roots and 1 stationary point. That'd be pretty easy. That'd be a parabola. Have 2 roots, 1 stationary point. Number 9, 3 roots and 1 stationary point. That would be impossible. And I talked with a few people about that, but if you're going to have just 1 stationary point, basically that means it's only going to turn around 1 time. So, and again, the key was in the problem, it talked about a differentiable function, which means it's got to be continuous also. So there's no jumps, there can't be gaps in it, things like that. Okay? So you got 1 stationary point, this would have 2 roots. The only way you're going to get another root if it turns back around. And to turn back around, it's going to have another stationary point. Okay? Now what if they would have left off the word differentiable in the instructions? What if they would have just said continuous? What could I do? I could come to a sharp point right here and then go up. And then I could have answered that question as true. That would have been an example. This would have 3 roots, and it would only have 1 stationary point, because here the derivative is undefined. Okay? So, again, that would be, some kind of question, I could ask, just getting at your understanding of differential. Okay? If the directions would have said continuous, we could have had that. If they had said differentiable, which they did, then it's not possible. It's not possible. Okay? Number 10, 1 root and 2 stationary points. Okay? 1 root and 2 stationary points means it can only cross the x-axis once. Okay? Well, you could have one of the turnaround points be there. There's 2 stationary points, but only 1 root. Okay? Number 11, infinitely many roots and infinitely many stationary points. What do you got there? Sine graph. Sine graph. Okay? And then we kind of skipped those other ones. You might look those over, though. You might think, look those over and try them. I mean, those would be other possible ones. I just kind of stopped at those other ones. Although, isn't 14 the same as 11? That's weird. Okay. All right. Let's look at 15 through 18 also, because this kind of relates to some stuff we did with the first 2 theorems. It'd be good to go back and look at those questions on intermediate value and extreme value. Those problems we talked about. Does the conclusion hold, and does it violate the theorem, and and those different ways of working those questions. But on 15, if you've got f of x equals absolute value of x, okay, which is the V graph, like so. Does f satisfy all hypotheses of the mean value theorem from -1 to 2? And we didn't do this one, but does f, that function, satisfy all the hypotheses of the mean value theorem from -1 to 2? No, because it's not differential. Not differential. It's continuous, but it's not differential. Does f satisfy the conclusion of the mean value theorem? From -1 to 2. Does? This is the kind of questions we had in the other one. It would not have to satisfy the conclusion of the mean value theorem because it's not differentiable, right? You didn't get the A, but you still could get the car, the conclusion, or the iPod, or whatever it was.
No.
Why not?
Because the slope is either -1 or 1. And the slope from -1 to 2 is 1/3.
Something different, right? It'd be good to draw in a little triangle here. If I was doing this question on the quiz, I would draw in, I would do exactly what you're saying. That slope is 1/3. I would draw in a little slope triangle there. I would draw in that slope between the endpoints. Or, in the absence of this, have 2, this y value is 2, this y value is 1, so 2 minus 1, and then 2 minus -1, and actually do the slope calculation. So one or the other. If you're dealing with the mean value theorem, the conclusion to the mean value theorem, because remember, the conclusion to the mean value theorem is this right here. The conclusion to the mean value theorem is this little formula. So when you have the mean value theorem, you're probably going to be doing, most of the time when you're asking a question about it, you're probably going to be doing some calculation, a slope calculation, and probably a derivative calculation. Okay? Not on this one that we're doing, but on a lot of them. 19 you would. Because that's the 2 parts to that theorem. But if you look at what Harry's saying here, is the slope between the 2 endpoints is 1/3. So somewhere in between there would have to be a slope of 1/3. But unfortunately on the V graph, the slopes are -1 there, and they're +1 there. They never equal 1/3. So the conclusion does not hold. Okay, in 17. Does f satisfy the hypothesis on the interval 1 to 2? Well, from 1 to 2, this function is continuous, and this function is differentiable, right? Between 1 and 2, it's not a horizontal diagonal line, so its derivative exists everywhere and all that good stuff. So the hypotheses are satisfied. So is the conclusion satisfied? Well, it has to be. If the hypothesis is that if you get the A in calculus, you have to get, the IPOP. It has to happen. Well, if this is differentiable, then yes, it has to equal. And then it says, okay, find the C. Well, what is the slope between the endpoints? 1. Where in there is the slope equal 1? Everywhere, right? So it says find a C. It says if so, find at least one suitable value of C. Well, anywhere in between 1 and 2 would be suitable. Okay? Now, actually don't include 1 or 2 though. Because it says a C in the interval A to B, so it can't equal one of the endpoints. But any point in here, the slope, the derivative, is going to be 1. All right, so that is how you could talk about the mean value theorem, kind of like we did with the other theorems with questions like that. Okay, 19 is a pretty typical one. You could probably expect some sort of question similar to this when it comes to the mean value theorem. They give you this function f. Okay, they ask you about the interval -1 to 1. Explain why there must be some C in this interval such that the line tangent to the graph of f at that point has a slope of 2. Of course, the slope of the tangent line is what? Slope of the tangent line is derivative. That's what derivative is. So I would start out in this problem by doing a derivative. Actually, you wouldn't even have to do a derivative because they already told you that it has a slope of 2 somewhere. So actually, I'm not even sure you need to do the derivative. Now, sometimes they'll word this question a little differently, and they'll give you, they'll tell you to find a certain point where it has that slope. Okay, so you do the derivative, set it equal to 2, and you solve it. Okay, and find where it is. But not on this one because it's going to be like a 6th degree, and you're probably not going to be able to solve it anyway. So what calculation would we do? The slope between the endpoints, right? What we want to do is the slope between the endpoints. Because what it says is explain why there must be a point C in that interval such that the line tangent to the graph has slope 2. Well, according to the mean value theorem. Now, key part about using the theorem is it's got to meet the hypothesis. Does that function meet the hypothesis? Why? How do you know? You'd have to talk about this. It's polynomial. Polynomial functions are nice and smooth like this. They're always differentiable. A polynomial function is always smooth, no sharp breaks, no jumps. So this function, because it's a polynomial, is differentiable. So it meets the hypothesis. So therefore, there has to be some place, if there's going to be some place that has a slope of 2, the slope between the endpoints better be 2. So what I would like to see on your paper is this. F of 1 minus f of -1. This would be a really good way to write it. If you had that on your paper, that would go a long ways towards getting the full credit for this one. Now you would have to say something about the polynomial functions, always differentiable. So that would have to be in there. You got to make sure the hypothesis is given. But they say explain why this must happen. It's because of the mean value theorem that it must happen. This is differentiable. We're going to do the slope between the endpoints really quick. Let's put a 1 in there. We get 1, -1. What do we get? 2, I think? Yeah. Put a -1 in there. What do you get? -2. And on the bottom we get 2. So this would be 2 plus 2. We get 4 over 2, which is 2. Okay? So you actually want to have that calculation on your paper. Okay? And it'll be a pretty easy problem like that, where you can plug a 1, plug a -1. You don't need a calculator to do that. Okay? So I hope you don't need a calculator to do that. So you got a 2. All right. So according to the mean value theorem, since it's differentiable, the slope between the endpoints is 2. There has to be some point C in between there that has a slope of 2. If that wouldn't have come out of 2, then we'd have been in trouble. Right? Then we wouldn't have known. Okay? Mean value theorem says slope between the endpoints has to be some point in there that has it. Okay, and then they did have a mistake in the back of the book when you go to number 33. What was it, Anna? They said it was no?
Yeah.
And it's supposed to be yes. Right? And the bottom line is, I think maybe we talked about this one other time. Did we talk about this one time with the fairs and the toll booths? You ever went through a toll booth? They have them down in Kansas on the interstates. And you get a ticket, and it's punched where you went through and what time you went through. Okay, or it's punched or it's barcoded or whatever. Then when you get off the interstate, and they charge you based on how far you went, right? And that's what they do instead of, that's one way of raising money instead of taxes to pay for the roads. They feel this might be more fair, is to actually make the people who actually are using the road help to pay for repairs and so forth. So that's why they do it. Okay, so you're driving on this toll road. They're a lot more common in the East Coast and stuff like that. But so when you get off, you hand them the ticket and they scan it or whatever, and they tell how far you went. Okay, and then they charge you then $1 or $1.50 or a couple, whatever, based on what you've done. Well, what they're saying here is that they could actually issue you a speeding ticket based on that. You know, you got on the interstate at this time, you go 100 miles, and you hand them the ticket, and it's only been an hour. Well, if you've averaged, so what are they saying? If you've averaged 100 miles an hour getting here, at some point you had to have been going 100 miles an hour, probably faster, but if you've averaged 100 miles an hour, at some point you had to have been going 100 miles an hour, so we're going to give you a speeding ticket for going 100 miles an hour. Now in this case it wasn't 100 miles an hour, what was it? 80, right? Because an hour 15, so that'd be 75 minutes or 1.25, right? 1.25 hours. And it was 100 miles down the road, so 100 divided by 1.25 is 80. So he went 80 miles. He went 100 miles in an hour and a quarter. That's an average of 80 miles an hour. So therefore, he had to have been going 80 miles an hour at some point. Because you can't get off. I mean, you couldn't say, well, there's no way getting off would have actually made you go slower too. So that wouldn't have helped any. I mean, there'd be no way around it. I mean, once you're on one of those toll roads, any exit you get off will have another toll booth, and they'll take your ticket and so forth. So I don't know if that's actually true. I don't know. I've never heard of that actually happening, that they actually would give you a speeding ticket based on, what happened. But what's that?
They'd have to explain this theorem to everyone.
Yeah, I'm sure the people that work there in those toll booths probably would quote the mean value theory. Yes. Well, in my calculus class, well, it's a tough job market though. Anyway, so then they have you figure the fine. But again, same kind of principles as other things. All right, if you look there on page 288 then, if we just continue on the next couple pages, they do give kind of a little summary of the chapter right there on page 288 and 289. Let's talk through that because that's one of the things this quiz tomorrow is about, is kind of the main ideas, what's going on here in chapter 4. So let me just walk through kind of the things I want you to make sure that you kind of brush up on, maybe look over, so you could ask questions about, or answer questions about. First paragraph there at the bottom of 288 says slope fields. Probably not much there on slope fields. About the only thing would be that section was about differential equations, right? A slope field is a graphical interpretation of the solution to a differential equation. So I may ask you just about differential equations in general, right? What is a differential equation? An equation with derivatives in it, right? That was very simply the explanation of differential equation. What's the solution to a differential equation? The original equation, if y prime is in your differential equation, then y equals would be your solution, right? It's not a number, it's the original equation. If it's f prime that's in your differential equation, then f equals would be your solution, right? So the solution to a differential equation is the original equation, okay? So those are just some of the basic ideas about differential equations, but not going to draw any slope fields or have to do any of that or actually solve any necessarily differential equation. Limits involving infinity and L'Hopital's rule, probably not going to be anything there about L'Hopital's rule or limits. I mean, we could calculate some without calculators easy enough, but we kind of did a quiz with those problems on it, so won't be anything on that. Optimization, extreme values. The only thing that would be in here, that was on our quiz we took, and then it was on this take-home quiz. You had those story problems, those kind of things. So we won't have any of those. But we did talk about where do you look for max and mins, right? Earlier today, we were talking about derivative of zero, derivatives undefined, endpoint, right? That kind of stuff. So explaining the process of optimization and that kind of stuff could certainly be, or what are critical points? You know, the derivative is zero or the derivative is undefined. What are stationary points? You know, those kind of definitions, those kind of things. You know, make sure you're understanding of those. The parametric equations, nothing really there. Again, that was mostly calculation stuff. I suppose I could ask you, what's the speed equation of a particle? Let's just say none of that. Let's say nothing on parametrics. Okay, nothing on parametrics. Related rates were really all about calculating, and you know those kind of problems we did a bunch of those on the take-home as well. So nothing on related rates. The next paragraph we actually completely skipped that section. That was 4 or 5, I think. We didn't even do that section. So don't worry about that stuff. Newton's method, I did say that I want you to be able to explain the idea of Newton's method and writing the tangent line and maybe something along the lines of the first homework question we had on those, which is a little bit like your one on the take-home quiz. You know, here's, you plug in this number and it takes you to this root, and you plug in this number and it takes you to a different root. What happened? Why? Explain why that. Why did Newton's method do that? So, you know, a picture of that can be helpful. Kind of like those pictures I showed you up here on the. Just pull one of those over. We talked about the butterfly effect on that a little bit. If I took sine, took a first guess, shoots me clear over there. That shoots me over to that one. And gives me that one. So what we found out is, as I move this around, depending, just small changes in that can shoot me to a lot of different roots. Okay, if we're just on kind of a pretty simple one, like this one, you know, ride the tangent line, see where the tangent line equals 0, go to here. You're not going to have to memorize the formula for Newton's method or do any calculations on Newton's method, but this process of finding where the tangent line equals 0 gets to be very close to where the actual function equals 0. And we use that to approximate. So just understanding that, that process. So those are some of the things in those earlier sections. And then we get to the last section, continuity and differentiability, and that's where we have the 3 theorems, and that's where we have the homework, the last 2 sections with the homework about those theorems and the different aspects of what those are, be able to state those theorems. Most of the questions, half or probably a little more, are going to be on those things. Okay. And then some other questions kind of picked and chosen from some of the other stuff we just discussed. Okay? All right. Any questions about the quiz for tomorrow? All right. Other than that, then, the rest of our week is going to be getting ready for the midterms on Friday and Monday. The first 2 packets will be due on Friday, sample 1 and sample 2. Okay? Those are the should be pretty much done. All right? Those are due Friday. And then the next 2, the one you have now, and then another one that I'll give you later, tomorrow maybe, those will be due on Monday. So that way you'll still have a couple of packets to be looking over, finishing up, whatever. Now we're going to spend a lot of time on that stuff Wednesday and Thursday, so should have time in class probably to work on that last packet. But if you need it, or spend some extra time over the weekend getting ready for the second midterm, you have that capability, and we'll hand those in on Monday. Okay. So if you have spent any time on exam 3, let's just take a little bit of time. It was exam 3, it was called, right? Or no, exam 2. It was exam 2. It was this one. Just says exam 2 at the top. Okay, the first 2 we got said sample, great big letters at the top. This is exam 2. Okay, anybody get a chance, if you've got a chance to work on any of this at all, anybody have any that you ran into that we could talk about?
We did 16.
16. Okay, now this packet, the sample 1 and sample 2 are a little newer than the exam 2, exam 3. I don't know if that makes a whole lot of difference. One difference was slope fields. Slope fields were not in the AP test when this packet was written, so you probably won't see any slope field questions on this. In the other packets, we did have a slope field question or two, I believe. Or, you know, so otherwise, they're pretty much the same thing. All right. If f of x equals e to the 2x and g of x equals natural log, then the derivative of f of g of x at x equals e, that's important right there, is what? So Anna, what do you think? What'd you try there?
Well, I just said e natural log of x to the 2x. So I just kind of like set it up.
Okay, and I think maybe, because f of g of x means like one function in another function, right?
Yeah.
Say that again.
So e and then parentheses, and then natural log of x, and then the parentheses, and then to the 2x.
Okay, that is just a little, that's where you went wrong. That's where you're not going to find that answer. Because what this is saying is take g of x, which you're right, is natural log of x, and plug it into the f function. But where do you plug it in? Where the x is.
Yeah.
So what we would want to do for this is, let's call it y. We'd have e to the 2, and then where the x was is where we want to plug in our natural log of x. That would be the secret to that. Now, even with that said, it's not automatically easy. Anybody have an idea what we would do next? Now, to be honest, I wouldn't even need those parentheses, and I really could just go e to the 2 ln x. Sometimes the parentheses actually
Then
could.
we just plug e in x. So that x equals.
No, because that's right. It wants the derivative at x equals e. So, and this is, I'm glad you said that, because this is important. If we say find, if they ever tell you find f prime of 1, you got to make sure that you don't plug in the 1 until you found f prime. And you've heard me say this before. Before we can find f prime of 1, we have to find f prime of x, right? Because then we have to have a place to plug the 1. If we plug the 1 in first, well, then we've just turned it into a constant, right? And then if you do the derivative, it's always going to be 0, right? You wouldn't, nothing would ever happen there. So we've got to do the derivative first. So how would you do the derivative of this?
E to the 2 natural log of x.
So the rule for e to the u is e to the u times u prime, right? So we get e to the 2 natural log of x times derivative of the inside, which would be derivative of 2 natural log of x, would just be the 2 would hang out here. The derivative of natural log is 1 over x. That'd be 2 over x. That's right. That'd be 2 over x. Right? Just like that. Then we could plug in our 1. What's natural log of 1?
X
No,
equals
you
e.
plug in.
Oh, I'm plugging in e. Thank you. Oh, okay. Yes. I thought you were answering my question. You were correcting. Good. Yes, plugging in e. So what is ln e?
1.
That's 1.
Oh.
So e, 2 times 1 is 2. So this is e to the second
E.
times, and then 2 over e.
So it's 2.
This e would cancel one of those e's,
C.
and it would be 2e. Now there actually was I think they put this in there for a reason. There was a simpler way. Once we got to here, there was something we could have done algebraically that would have made life a lot easier. But if you know your derivative rules, should have been no problem. 2e. But what could we have done right here? Y equals e to the 2 ln x. What's one of the advanced math things you can do with 2 ln x? When you've got a number in front, no, not quite put it out front. When you've got the 2 in front of a log, I'm recording this. If I've got log, let me write the actual rule. Log base b, a to the n power. What can I do? I can bring the
n in front.
n and bring it down in
Constant.
front.
Constant.
So if I can do that, can I do it in reverse? If I've got a constant down in front, I can bring it up as a power. So we come back to here. I can bring the 2 and put it in there. I haven't done a derivative yet, so this is e raised to the ln x squared. What do you know about e and ln? Cancel each other out. They're inverse functions, like square and square root. So e to the ln x squared is actually equal to y equals x squared. What's the derivative of x squared? 2x. Now plug in an e. 2e. So, you're talking about a time saver, because there's 2 minutes, on the thing. There's like 2 minutes per question. We talked about that the other day, didn't we? We talked about that kind of time. Now, to be honest, in the midterm, it isn't quite as much of a time factor because I'm throwing the multiple choice or the free response in with them, and you usually get plenty of time on the free response. In other words, if you know how to do it, you usually got plenty of time. And to be honest, sometimes on the free response, there's parts you won't. There'll be parts of some problems that some people won't know how to do, and so you'll skip that, and then you'll end up having extra time, So it's not really a good thing to have extra time because that usually means there's a bunch of problems you didn't know how to do, okay? But it depends how much work you're putting into the packets and how much of this you're doing. But that would be a time saver right there. If you saw that when you plugged it in, makes your derivative a little easier and so forth. If you didn't, no problem, you still can get it. Okay? What else? 19.
It's just a derivative, but I did it like 5 times and
It never could go yet. Well, yeah, it's just a derivative. Well, there's a lot of people on the gateway test that would say that just a derivative is not necessarily an easy thing to do, right? Just doing a derivative. And it's a lot of algebra, quite honestly. It's a lot of algebra is what it is. So if we call that y, I see and here's another thing, on the multiple choice, look at, just at least take a peek at the answers, see what format they're in. That usually, or often, can give you a little bit of a hint as to what to do. Okay, so I'm definitely going to want to put these into that format. So square root of x is x to the 1/2. Now this one, I just got some algebra. This is x to the first, and this is x to the what?
1/3.
1/3. Now x to the first times x to the 1/3, we do what with the powers? We'd add. Power on a power, we multiply. Multiplying, base is the same, we add the powers. That's x to the 4/3, but it's on the bottom, so it's x to the negative 4/3. So really, the key to doing this one properly is getting that written properly. And you're erasing already, so that must have been it. Yeah.
Because I had it in the product rule, and I went ahead and used super well.
Oh.
And I could add them.
I'm glad you said that. One of the common difficulties on any derivative problem involving quotient rule and product rule is we use the quotient and the product rule when we don't need to. And almost invariably we do it wrong. Now it still should work. What Anna did by doing the x and the x to the 1/3 and doing a product rule on those should still work. You should be able to do a product rule, but it's going to get much messier algebraically. And it's just going to be really hard to do because then you're going to have a sum, and then because the product rule is a sum, and then it's on the bottom, so it's going to be the whole sum to the -1. So then you're going to have to do that, and it's just going to be a real mess. And getting it back to the way our answers look will really be hard. Okay. Now again, the other lesson I have on that quotient rule thing is this: if I have sine x over 7, or I have 7 over sine x. In neither of those cases would I recommend doing the quotient rule.
Just. He was here
1b. Neither one of these cases should you do the quotient rule. In this one down here, you should make this sine x to the -1 and do your, bring the -1 down in front and do all that. On this one, you should make this 1/7 sine x, and then that's even easier. Then it's just 1/7 cosine x, right? So make sure, you don't do things unnecessarily. Well, anyway, back to this one. We get 1/2 x to the -1/2. Bring the negative. Yeah, now it's pretty easy, isn't it? So we get a positive 4/3 x to the what? We subtract 1 and we subtract 3/3. So that'd be -7/3. So B. All right. Well, I don't know how many people have spent much time on this, so I'm going to go ahead and give you work time. Now, you can use that time to review for tomorrow's quiz or work on this packet. Okay? Tomorrow after the quiz, you'll have work time for this packet if you have any time after the quiz. And I'll probably also be handing out the next packet as well. We will have most of Wednesday and Thursday to work on that last packet. Okay? So if you get this one done by then, that would be good. The answer books for these older packets are these white books here. Okay? I've got a couple of those. All right, and if you've got some additional questions on the packet, I will certainly help you with those. All right, go ahead and get to work.
As you on the last one.